Standard enthalpy of formation is yet another way to calculate the enthalpy of a reaction. It allows us to use tabulated data in order to figure out the enthalpy of reaction without actually doing the experiment. The heat of formation is defined as the enthalpy change for a reaction where exactly 1 mole of a substance is formed from free elements in their most stable standard states under standard state conditions. This superscript naught symbol refers to standard state conditions. Standard state conditions are for a gas, 1 atmosphere of pressure, and for a solution, 1 molar solutions. The temperature is often ran at 25 degrees Celsius, which is 298 Kelvin. The subscript F stands for formation, meaning we're forming 1 mole of that substance, whatever it is, from elements in their stable standard states. We'll look at a table in a second. The delta H for an element in its most stable standard state is assigned as 0 kilojoules per mole. We're going to use these values in order to determine the enthalpy of a reaction by following this formula. The heat of the reaction can be calculated by taking the sum of the heat of formation of the products times any coefficients from their balanced chemical equation minus the sum of the heat of formation of the reactants also times any balanced coefficients. The following shows a short version of the standard enthalpies of formation for some substances. You can find a long list at the back of your textbook, as well as there's a much more full handout online for you to print off and keep by you. If we look at these, they're listed as our amount of heat that's absorbed or released in kilojoules per mole for forming 1 mole of whatever substance is listed. The heat of formation for many substances is going to be 0. For elements in their most stable state, such as solid carbon in the form of graphite, solid silver has a 0 heat of formation. Nitrogen is a diatomic molecule, so it occurs naturally as gaseous N2. The heat of formation for that would be assigned 0. Same thing with I2. It occurs naturally like that as a solid, so its heat of formation is 0. That means when we take all of these elements in their standard state and we use them to combine to make different compounds, the heat of formation will either be absorbed or released, and it can be measured. We can use these tabulated values in order to calculate the enthalpy for a reaction using the chemical equation we saw on the last page. Let's try an example using standard enthalpy of formation values. Determine the enthalpy change in kilojoules for the reaction using the tabulated heat of formation values. 2 moles of solid iron react with 6 moles of aqueous hydrochloric acid to produce 2 moles of aqueous iron 3 chloride and 3 moles of gaseous hydrogen. We want to figure out what the heat of reaction is for this chemical equation. And below are listed the heat of formation values for all of the substances within the reaction. We could look these up if they weren't supplied for us. So following our equation, we're going to take the heat of formation for all of our products and subtract off the sum of the heat of formation for all of our reactants. We also want to take into account what the coefficients are in the balanced chemical equation. So that means we're going to have 2 moles times the heat of formation for aqueous FeCl3 plus 3 moles times the heat of formation for gaseous H2, the sum of the products minus the sum of the reactants, so 2 moles times the heat of formation for solid iron plus 6 moles times the heat of formation for aqueous HCl. It's important that we keep track of the states of matter because there would be a different heat of formation for aqueous hydrochloric acid as there would be for gaseous hydrogen chloride. Notice that the heats of formation for H2 gas is 0 kilojoules per mole, as well as the heat of formation for solid iron is 0 kilojoules per mole. That's because the heat of formation is assigned as 0 for elements in their standard, most stable states. So plugging in the values for iron 3 chloride, we have 2 moles times our heat of formation for iron 3 chloride, which is negative 549.9 kilojoules per mole, plus we would have 3 times 0, so just 0 kilojoules for our heat of formation for hydrogen, minus, we're going to have 2 times 0 for our heat of formation for iron, so that would just give us 0 kilojoules for the iron, plus 6 moles times the heat of formation for aqueous hydrochloric acid, which is negative 167.2 kilojoules per mole. And when we calculate our delta H for this reaction, notice our units of moles are going to cancel in each case, and we'll be just left with units of kilojoules. We should get negative 96.6 kilojoules for this reaction.